Um, but anyway, getting into the stuff for the chapter this week, we were reading chapter 6. We were extending from the previous chapter. So the last chapter, we manually defined a linear regression setup. We just said, here's our weight, here's our bias. We're going to multiply it by this input. We're trying to map to this output, and we're trying to learn what the correct weights and biases are through backpropagation and various other techniques, but eventually building into backpropagation. And so in this chapter, what we're doing is we're extending and we're learning the building blocks to actually make a more complicated neural network. And the motivation here, why would we not just use linear regression, is neural networks can be used to approximate anything, basically. So you don't have to know that your data is linear or quadratic or sinusoidal or some other pattern. You're able to just say, okay, give it to a neural network, you figure out what my assumption should be, what the output function should look like. And so looking at these artificial neural networks, they're loosely motivated by biological neural networks. We've kind of faded away from that. People try not to use it's actually a brain thing that they used to at one point. There is an entirely separate area that people are trying to simulate the brain more closely, where they're actually using spiking neural networks and doing all kinds of different stuff. So the artificial neural networks that we're looking at here are not necessarily that. It's just a mathematical function, and we don't necessarily draw too much from the biology of it. And so the basic building block in this neural network is a single neuron. And in this case, it's just built out of a weight and a bias. And so that's like in the last one, we had a single input, we had a single weight and a single bias. Our neuron was just that weight and bias pair. And so neural networks, universal function approximator is what a lot of people call them, because it's able to approximate any function, and it makes them very powerful. One of the things that makes them really powerful is the activation function. So if we actually just purely stacked a whole bunch of those linear regressions together, like we did from the previous chapter, we made one linear regression. If we just said, okay, let's just make 2 of them, it actually wouldn't give us anything that's that interesting. We need the nonlinearity in between the layers in order to be able to do that universal function approximation that lets us figure out basically any input and map it to an output. And so we'll talk a little bit more about activation functions in a second. And so we can stack those together, and through the magic of backpropagation and the chain rule, we can just figure out the weights, and PyTorch handles all of that for us. And one thing to note is, if you talk to a statistician or an actuary or somewhere in a different line, they have a lot of different conversations about guarantees of convergence and the different properties and the assumptions that they're making and all kinds of stuff like that. And a lot of those kind of go out the window when we start talking about neural networks. We don't have guarantees of convergence to the global optima and stuff like that. So just something to keep in mind. People might be having conversations about, oh, did you check if your output has some certain characteristic? And typically with neural networks, we don't really care that much. And so getting into activation functions, they gave us a few different examples. I kind of just highlighted the ones that I think are actually useful and pertinent. One of them being the sigmoid, and sometimes called the logistic function. And so what this does is it basically crushes whatever output you have to a range of 0 and 1. And this is useful because it can pose something as a classification. So it can output a probability. So typically your neural network, if we're thinking about like the last one we were looking at, where we have the simple linear regression, and it's just you multiply something by the input and then you add a bias term. that can be completely unbounded. That can output 30,000, for example. But a lot of the time, you actually want a constrained range on your output. So if you're trying to predict cat or dog and bear, you can have neurons for each of those outputs and then apply a sigmoid layer. And then instead of saying, okay, well, this bear got a 30,000 and cat got a 10 and um, whatever other animal I said got a zero 0.1, you can apply a sigmoid and then it will crush it down to a range of 0 and 1. And you can sort of interpret it as something sort of like a probability. It's not necessarily exactly a probability, but you can tell, okay, the bear with its 30,000, that gets crushed down to 0.999 whatever. We can say it's fairly confident that it was actually a bear in the picture that you were looking at. And so the sigmoid is useful for that reason. People used to use it in the intermediate layers, but now basically everyone just uses it as a final layer to map to a classification task. People don't really use this for intermediate layers that much anymore. And then there's tanh, which is, I believe it was used even before the sigmoid. And people don't use it very often anymore. I think it's sometimes used in LSTMs and various other things. But for the most part, most people use Rayleigh or some version of it. So it's rectified linear unit is the full acronym for it. And this is a very simple function that basically says we'll take the max of 0 and whatever its input was. So everything on this side is just 0, and then everything beyond that is just whatever the input value was. So if this value is 30,000, then it's over here 30,000, and if it's negative 30,000, then it's just 0. And so the bend in this graph is what gives it the nonlinearity. And a lot of people use this as a default now because it's proven to work pretty well. It's fast to calculate, and it has pretty good convergent properties. New activation functions have popped up, and people have argued, oh, this is the best, this other one's the best. But the benefits I've seen have been relatively minimal. So in the book, they were talking about what are good properties of an activation function, and so they were highlighting nonlinearity and differentiability, and then the ones that I kind of added in are speed of calculation, because you don't want an activation function that's used all throughout your neural network to slow you down by any amount. You want it to be something that really is not a significant piece of your calculation. And then you also want convergent properties. So sometimes you might find an activation function that converges faster, but it gets to a worse minima, or you might get something that converges more slowly, but gets you to a better final minima, or you get something that just half of the time it blows up and it doesn't get you a good result. So there's lots of different things there. One of the things I wanted to show is this repository that this researcher put together. And the partial goal is to say, hey, my activation function is the best. So that's part of the goal. But the good thing about this is they also have a very extensive collection of all of the different activation functions compared on a single task. So you can see this is their activation function, MISH, and it gets this mean loss, so lower is better. And you can see this is compared against all of these. So Rayleigh gets very, very slightly worse than the activation function that they claim. So if you're ever curious, you can look at this and you can see what the results are. And they also measure like the standard deviation. So like I was saying, you might have an activation function that sometimes gets amazing results and sometimes just doesn't converge at all. And so you're also looking for advantageous properties in multiple different directions. That's kind of going deeper than the book, though. For the most part, you won't have to worry about that too much. Just using Rayleigh and Sigmoid, you'll get decent results.
Hey, Ryan, can I
Yeah.
make a quick comment slash question? So I'm not remotely an expert in this area, but it seems to me that for good convergence, one of the things you need is you need some region of the activation function where the slope is 0 or very small, such that changes won't really cause much update to the weights. So basically, if you're saying, hey, this particular, node is trying to pick out this one particular thing, that it kind of gets ignored everywhere else,
Mhm.
and then you need a region. Obviously you need at least one region somewhere where the slope is reasonable, and therefore it can learn, because um, any gradient that's propagated back is going to tweak the weights up or down.
Yeah.
Does
Yeah.
that sound right?
Yeah. So if they mention that in the book with the classification example. So if you have something and it's got a weight of something massive, 10,000 or something like that, it gets crushed by that sigmoid unit or whatever your activation function is, and then it becomes close to 500. And you know, okay, this is just a big weight. It doesn't matter really how big. We know that this whole region is probably bare or something like that. And then the part where it's still discriminating back near zero through one, you know that that is actually things being moved around and learned still.
Thanks, Ted. I think that that's a nice intuition as to why like Rayleigh might work better than Sigmoid. I think gives a good understanding of, since Rayleigh gets to 0, then you have less bump in those weights, so it converges faster. Thanks for that.
Yeah, and I think one other thing is that, like, Rayleigh might not be the activation function you would want if you were forced to only build shallow networks. If you could only have one hidden layer, or maybe at most 2 hidden layers. But I think that because we're now able to do deep networks, some of the other properties of that curve on the sigmoid, you can get just by stacking layers instead of having to have that built into your activation function. And then I think, to Ryan's point, I don't think the book mentioned, but Rayleigh is just so much screamingly faster to calculate than sigmoid. So that benefit, you might be able to, for example, add a whole nother layer at the same amount of training time, and you're going to get more value out of having that extra layer than you would from having a slightly more interesting shaped activation.
And there's another advantage is that of that speed is you could train 2 or 3 or 4 times, and that resetting and restarting and re-randomizing all your weights before you start, that lottery ticket hypothesis comes in. And that variance of the ReLU is actually a good thing, because you want it to, that variance can sometimes be in your favor. Sometimes the error can be extremely small in some cases. And so, yeah, for companies like Google, where they can train a lot of models and they want to train a lot of models and try to do a lot of hyperparameter optimization, ReLU is a good choice.
Are there any approaches that kind of parameterize what activation function you're using, so you can maybe test that more efficiently? Is anyone aware?
There's been a lot of research on this because it's kind of fundamental to every neural network. So people have researched it pretty thoroughly, and Google has done some work doing a sort of evolution thing where they tried to make it evolve its own what's it called, activation function, and figure out where do the different activation functions go and stuff like that. And I would say that the activation function just doesn't honestly matter that much. There are gains to be had there, but it's on the scale of 1 or 2%. It's not something that really should be a massive focus.
Not worth the effort of testing that thoroughly. Just pick one and move on. You'll be okay.
Yeah, yeah. I other people have different opinions than me. I've gotten in debates with people about this, but my personal opinion is you're probably better suited spending more time understanding the best representation of your data than you are tuning activation functions. That's at least been my experience, and I've worked on the competition stuff where even the tiniest advantage is very crucial. No one, I've never seen a write-up where someone said the reason they won is because of some special activation function they used. So that's at least my opinion on it.
So if I could just add a quick comment, Ryan, I wholeheartedly agree, and I will say, if anyone in this audience is aspiring to be a researcher, then maybe you do, you know. But like if you're building a CNN, like, you know, there are dozens, if not more, people who have experimented with different activation functions on CNNs. And so if you see, you know, 4 different state-of-the-art networks, and they're all using the same, or maybe just ever so slightly different activation function, I don't think there's a lot of juice to saying, what if I tried some different activation function? I bet it's going to revolutionize, you know, computer vision. Probably not.
I tried different activation functions, and I learned that ReLU is much faster. So when it takes for ReLU several seconds, it can take for Sigmoid or hyperbolic tangent a few minutes, which means that if you do competition set, which can, you know, easily take several hours to compute even with GPUs, well, it can turn into days, and it is just waste of time for a really big set for a really deep neural network.
Mm-hmm.
Ted, this is just out of curiosity because I agree. I'll probably just going to go with ReLU anyways. But you had mentioned how for shallow networks, Sigmoid might be more advantageous, and I was curious if you could kind of go a little bit into more of your thoughts on that.
So in the book, they have a picture they show where they composite 2 potential different functions, right? They do A and B, and then they do C and D, and then they do all of them together. Hold on a second. All right. So do you guys see, this is page 150.
Yeah.
Okay. So when they do this combination, you know, C, A and B, and then, you know, in the next layer C and D or whatever, like, so you got this function, but basically, right, you got 1 upward bump and 2 downward bumps. So you can imagine that if you had like 2 hidden layers, whatever, I mean, like, you can only get so many squiggles on this with 2 layers. But essentially, ReLU is linear. It's just sort of got like a left and a right, right? Whereas Sigmoid is more non-linear, and so you can, you know, maybe get a little bit more shape, you know, out of this. So you can imagine that maybe if you were in the early days when you only had enough computing horsepower to, like, in a week calculate 1 hidden layer, that had they had the thought of, let's try using ReLU as the activation, I'm guessing it probably wouldn't have worked very well. You know, just you need a deep network in order to get, you know, the far more interesting shape. So even imagine just something not like super crazy complex, but just like you're predicting something and it's a parabola. You know, you need a lot of lines to stack up in order to build that shape.
Yeah, that makes a lot of sense. Thank you for the clarification.
So Ted, just jumping on the end of that conversation, this is Stephen, and I apologize, I'm outside, so if you guys hear wind noise, just let me know. But so if you were doing something that was at the edge, on an edge device, then that might become a consideration, what you just said, right? That I want to have a minimal number of layers as possible so that the speed of my of my ML is as fast as it can be on as lightweight a device as it can be.
Yeah, maybe. I mean, now I'm not the expert on this, so now I'm really just, you know, pushing the boundaries. I would guess that if you had sort of infinite resources, infinite time to experiment with different networks, that somehow you could build a smaller network, maybe with a with a sigmoid type activation function. They have, Ryan, do you remember what it's called? The one that's not an actual sigmoid, but it's just like a couple lines, so it's approximating the sigmoid, but it's faster.
No, I don't remember that.
All right. I forget what it's called, but they have one where, again, it's just made up of like whatever 6 line segments, and so it's faster, quite a bit faster than sigmoid. But it's still S-shaped. Anyway, but for practical purposes, I'm guessing it's probably not worth it to bother with that. Just, you know, just build the best thing you can, and then there's a whole area of, right, how do you prune networks and whatnot, and shrink them onto small devices.
I haven't read it recently, but before this current book, I was reading one called Tiny ML, and it's all focused on edge device stuff, basically, and various kind of simple Arduino, Raspberry Pi style computing things. And the whole goal is to train a neural network, push it to some tiny little device, and still be able to get decent performance out of it, whether that be lots of frames per second or decent performance out of a small footprint. And so I didn't get super far in the book, but they never mentioned anything in terms of activation functions or anything like that. It was mostly just how do we actually optimize this network to be the minimum layers, or the minimum number of neurons, or the minimum number of weights that we can prune away at the end. So it's a whole area of study. I don't know that we definitively have an answer on what's the best activation function. I think there's probably trade-offs in terms of Rayleigh might be the fastest to calculate, so that might afford you some different flexibility than Sigmoid, which might allow you less layers potentially. It just depends. It's kind of hard to speculate without doing some experimentation.
Okay, fair enough. Thank you.
I forgot.
Hey, Ryan, I see a question in the chat about Leaky Rayleigh.
Yeah, that's what I was going back to. I forgot that you had grabbed the screen. So Leaky Rayleigh is similar to Rayleigh in that instead of having that kind of flat and then max, it's just slightly angled down. So instead of just always being 0, it's angled slightly down. And what that allows is there's this belief in kind of dead neurons. And so if you have something that ends up on the side of 0, then it's essentially just getting no gradient and it can never move again. And so having it slightly angled, it still potentially has a way to exit out of there and go back to the other side. And it potentially gives you a little bit more signal. And that seems to be the case here too. Even in their experimentation, when we compare Rayleigh versus Leaky Rayleigh, it gets a tiny bit better. And it even shows that it kind of meaningfully reduces the standard deviation of the accuracy. So this is another one of the possible ones that you can just plug in with PyTorch. It's built in. So if you want to set your default to this, then go for it. No one's going to argue with that. But I mean, I'm not going to care too much about a 0.02 or a 0.2 difference in accuracy necessarily.
I'm not sure if this is outside of the scope of our discussion, so this can be saved for a later chat, but I am very curious about the usefulness of the p-values and the 95% confidence interval in regards to what we do with the machine learning side. Alexa, I don't know if that if it's a conversation for now, but
So there's a little backstory behind this repository. So this is actually a young researcher who decided to go out and do the most thorough study of what's it called, activation functions, because people were disagreeing with him, saying that his activation function actually wasn't that good. And so this is him all backing up that his is the best possible. And so he did all of these things basically in an attempt to prove that. And so this is him gathering additional evidence. I don't know that I would ever look at these and actually find anything meaningful out of them.
But to the extent that he's reporting this, Tommy, he's trying to support that he didn't just cherry pick a bad run for Rayleigh, right?
yeah, that makes sense when Ryan said that this is a study of the activation functions. That now it makes sense. Still, like, how does this? I don't understand how he's calculating these. Okay.
Mm-hmm.
Yeah. So you run it 23 times, and he says, "Here's I'm reporting what's the average, the mean of all of those runs," and then you can see how widely they're spread. And so he's trying to demonstrate that he didn't cherry pick that. Like if this were a TV commercial, right? Be like, oh, and the Ford, was the slowest in the whatever race, but the Chevy was wonderful.
Mm-hmm.
I hope we have no statisticians here, but the thing is that p-value comes from statistics. And for this to be reliable for analysis, we should have data which possess specific properties which are described in statistics. And the thing is that quite often our data is not quite aligned with these rules. So in this case, computed p-value is not very reliable, but statisticians who learn for years to respect p-value, they get very upset if you say it. So never say it to statistician first. And second, you see here confidence interval, the same goes to confidence interval. What is much more reliable is what is usually used in data science, meaning that it is a mean loss, mean accuracy, standard deviation of accuracy, more or less useful. But probably, if you write an article and you know that statisticians are going to read it, then putting in p-value, is more or less polite thing to do, I'd say.
Confidence interval is really pretty wide too. Actually, I don't know if it's worth even.
Yeah, it looks like he only did 23 runs, so it's not a very large sample. But of course, if you look at how many activation functions, you can understand why he wasn't going to do 200 runs of each one, right? But yeah. So you're assuming sort of like a normal distribution, and I don't even know if in this case you'd be assuming more than that.
Right.
There are actually four different
homoscedasticity
assumptions. There are 4 different assumptions, and normal distribution is the simplest one, which more or less understandable. They have other things. Like I am not sure I can pronounce it, but it is something like Herodasticity, something like this.
Yeah, homoscedasticity.
Oh my!
I can't say.
So
yeah,
good thing that you can say. Okay.
Yeah.
Anyway, the thing is that when we consider our data and work with it, then even if you do usual, ancient, no, not ancient, anyway, even if you do logistic regression, the thing is that you can get good results, good accuracy, even if your data does not exactly satisfy these requirements, because the only thing we can get from statistics that if it satisfies the requirements, that yes, we can get reliable p-value and confidence interval and what else, Cohen's score, anyway. But the thing is, if data does not obey to all these rules, it doesn't mean that we don't get a good model. It just means that statistics cannot say us anything about it. So what is much more practical is compute, well, this usual data science statistics. I mean, they're not statistics. Anyway, or technically they're statistics, accuracy and loss and, well, anyway, all these first 3 columns is what is usually crucial here.
Mm-hmm.
This
Yeah.
is my point. But don't quote me on this and never say it to a statistician. Okay?
Thanks, Maya.
You're welcome.
So I think going into the actual code, this whole notebook, the first one, is very similar to the previous ones we've looked at. It's looking at the same data, it's just now trying to do a neural network instead of the linear regression that we manually set up last time. So I'll kind of skip over some of this. I'll just do a quick run through. So we're importing NumPy, we're importing Torch, we've got our data. This is the inputs, this is the outputs we're trying to map to. We're plugging it into a Torch tensor. We're measuring the number of samples, we're taking the indices and we're shuffling them, and then we're splitting it into the training set and the validation set. So these are the indices for the training set and the validation set. And then we're going to actually grab that from the inputs, the outputs. We need to grab the indices for both of those, then the inputs and the outputs for the validation. And then we're importing this torch.nn module that we've been talking about. This is kind of the most, or I don't think we've actually gotten to that portion. Yeah, we'll just run through the code. I think that'll be the best way to learn that, actually. So this NN module is where all of the interesting neural network stuff is. It's got all the loss functions and the layers and the CNN stuff and whatever else you want. It's mostly in there. So setting up a model that matches what we did in the previous one, we just want a single weight and a single bias. What we can do is we can say nn.linear. And so this will make a single linear layer. And it has one input and it has one output is what that's saying. And then on top of that, the additional thing that we're looking at is, do we want a bias term or not? And by default, it has a bias term, so we don't have to worry about that. So this is perfectly capturing exactly what we were training in the previous one, but we just manually defined, here's the mathematical equation, and it's just kind of wrapped up in this linear layer. We don't have to define all of the math next time.
Ryan?
Yeah.
What did you just do to have that pop up?
I did Shift Tab. Yeah, that's a little Jupyter Notebook hack.
Got it. Thank you.
I did not know that either. Thank you.
Yeah.
And that works in full Jupyter. So if you're like on Kaggle or other places that are implementing notebooks, it doesn't always work.
It actually does work on Kaggle, but it has a bug and it will show up the text box at the top of the screen. So most people think it doesn't work. It does actually work, but it will put this text box all the way at the top of your notebook. So you can still look at it, but it's broken for some reason. Just an additional tip. So I actually use this all the time. And what this is returning is the doc string. So it's telling you what the input is, so all of the different arguments there. But if someone writes a doc string, it will also tell you all of the stuff that they wrote, basically. So they might have additional notes, like even here they have an example of some code, how you would lay it out. So I find that to be really useful.
Okay, one more time, please. Is this what? Shift?
Shift Tab.
Shift Tab. Okay, thank you.
Yeah. And this is kind of the value of the group for me, is I learned this from someone else a couple years ago because I had never known it, and then I saw someone do it and I had the exact same revelation. I was like, wait, how'd you do that? So I'm glad I can pass that along to you all. Defining the linear layer, one input, one output, and then we've got our linear model now, and now we pass it some input, and then it will make some output for us. And we can inspect the weights. This is kind of the same as what we were doing before, but before we had manually defined, okay, here's our parameters. Inside of our parameters is our weight and our bias. Now it's just all wrapped up into our linear model. And we can inspect this and see, okay, this is what our weight got randomly initialized to. This is what our bias got randomly initialized to. We can see the gradient calculation is turned on. And then after that, we can plug in random values. One of the things that they were highlighting is you typically want your inputs to be batches. So you always need your first dimension to be your batch. So if you have 10 examples, like we have in this case, we have 10 ones. And so its output will then be 10 times whatever these things are. 10 repeated times, not multiplied by 10, just to make that clear. And so similar to last time, we've got our linear model. We plug it into the optimizer. We tell it which parameters to optimize. We tell it what learning rate we want. And then if we ever want to inspect things, we can show what the parameters are. And I think they show it somewhere, maybe down here, that you can actually show the names and the sizes, so you can kind of print it all out and say, okay, does this make sense, what I just constructed? I'm seeing messages. Are there questions?
No, a cool link for Jupyter tips.
So they define a training loop. This is similar to the previous ones. Basically, they're saying we want to iterate over the data, the number of epochs, number of times. We want to make predictions with our model. We want to measure those predictions, how close were those to the correct thing, measure it with our loss function. And then we keep one loss for our training set, make predictions on our validation set, measure the loss of our validation set. And then we want to zero out our optimizer and take the backward step, but only for the training set, because we don't want to optimize for the validation set. And then we want to actually take the step and update the weights. And so this is almost exactly the same as last week. The only thing that's changed is the way we defined our model is with the torch.nn module, instead of the manually defined model that we had made earlier. And then the other thing that we can eventually move away from is we don't have to use this custom loss function we defined. So one nice thing in PyTorch is we can just define any loss function willy-nilly as long as it's differentiable. But Torch also comes with various different loss functions, so you don't always have to write out the full formula for all of the different ones that are fairly common, like mean squared error. So this is showing the actual training process. We can see the training losses going down over time, the validation losses going down over time. If you kept training this might eventually change, so the training loss is lower than the validation loss, but you need to run that for a little bit longer. So now they're showing the sequential method. So what we did in the previous one is we just said, okay, this single linear layer is our model. But with neural networks, typically you want to stack multiple linear layers, maybe convolutions, maybe LSTMs, maybe all kinds of different things. So you want all of these things stacked together and fed one into the other. And so the way you do this, one way is using the NN sequential. And so what this is doing is, you know that it's just one layer after the other. It's just a stack of them. And so you can say, okay, let's do a linear layer. We know we have one input variable. We want 13 intermediate neurons. We want to use the tanh function. And then we want our 13 intermediate neurons to map down to one final output prediction. And so this whole model now is all of these layers put together.
I think something that I guess is interesting from Keras is that, so we don't have to, we just define the features that are there, not necessarily the batch sizes with linear or those first functions. And that's always the case. You just say how many features you have and then how many neurons.
Mm-hmm. Yeah.
Okay.
Yeah. So for anyone who's used Keras before, the one difficulty here is you have to define the intermediate step. So Keras, you'll just say, okay, I want it to have this many inputs and then connect everything up. And then it will just figure out, okay, this is how many need to go everywhere for everything to match together. In PyTorch, you have to know how different things match up. So we can set this to 13 and you could set this to 12, but it's not going to work, because you need 13 output neurons to map to 13 input neurons here. And in Keras, you don't have that option. You just say generally, how many layers do you want in this layer? And it will just kind of map them together. So just something to be aware of. This gets a little bit more hairy when you start doing convolutions and other things. And it's like, okay, the output of this is going to be 3 pixels less than the other one, and I need to know what the final size is going to be on these various different things. So just...
I'm sorry, then I just got confused because you're right, it does say features here, but yet what, a half a page or something, it said batch size. So help clarify when the batch size is used and then why it's now features, because I thought I read something about that it is batch size, not features.
So this is a matrix here, and we're saying that we want a matrix that maps from one input feature to 13 output features. So this is defining the size of the matrix. And then the batch size can be actually anything. It could be a single point, or it could be 100 points, or it could be 1,000 points. And we're just going to broadcast that matrix to all of those points potentially. But what they were saying in the earlier one is you can't have it just be a single point. You would need it to have a batch size of 1 and then a feature amount of 1. So if we're looking at torch.ones,
you need an S on your 1.
Yeah. So this is saying that the dimension is just 1. And so that actually, it might work. I don't know this for certain, but it's not what you want. You could pass that to a neural network and it might be able to do something on it, but it's not really what you want. What you actually want would be something like that. And so this is saying that the batch size is 1 and the number of features is 1. Does that clarify a little bit? Because this number of input features cares about this dimension.
I don't know. Let me try one more time, and then if that doesn't work, I'll just sit on it for a while. So in the book where it says line 15, and I think your numbers are off a little bit, so the previous one to where you were, it starts off training loop, epochs 3000, optimizer. There we go. So yeah, one of those. So at beginning of, yes, your block 15, it says linear model equals nn.linear 1, 1. So that first, I think the first one was the batch size, correct?
That's the input features. That's how many input features there are.
Okay.
And the
I'm
number.
gonna let it go then. I thought it was batch. I must have read something wrong.
So
I'll go.
you don't have to do anything in terms of your model definition in reference to batch size. It will just always be broadcast to whatever batch size you pass it. So you don't have to worry about that really. So this is just concerned with the number of features.
So if I could paraphrase Ryan, in PyTorch, batch is mostly always handled for you, but the two places where you need to explicitly manage that extra dimension on your tensors is when you're shoving input into it, and when you're pulling input out of it, you explicitly have that far left dimension, which is batch size. But within the neural network and within defining your network and all that stuff, you can pretend it's not there. It's auto handled. Is that an accurate?
Yeah.
So so one thing that I think it may become, oh no, so this is the network of 13 units. So I don't remember, I don't think the authors really went into they didn't explicitly say this, but when you are building a simple neural network, what we call dense layers, they're fully connected layers. It means that from the first layer, the output of every single neuron is connected to the input of every neuron in the next layer. So that means that, for example, in this case, if the first layer has 13 neurons, then there are going to be 13 distinct outputs. And that means that the next layer has to be prepared to have 13 inputs. So this has nothing really to, so when they say features here, okay, so if you look at the output of Ryan's box 16, you'll see that layer number 0, it has one input. And so each of the 13 units gets that identical one input. Because there are 13 of them collectively, that layer, which I think PyTorch calls module, that layer has 13 total outputs, which it calls features. These are the features that will then be inputs for the next layer. So each individual neural network unit only has one output, but because there are 13 of them collectively, that layer has 13 outputs. And that's why after it goes through the activation, in this case, hyperbolic tangent, you're going to be left with a 13-dimensional tensor. Oh, sorry, not 13-dimensional, a one-dimensional tensor with 13 values. And so those 13 values are going to be copied to each of the units in the layer that's number 2 at the bottom there. And that's why that 2 says linear with input feature size 13. It's one-dimensional. Later on, we'll see CNNs. It'll have multiple dimensions, so there'll be a comma in there. I don't know if that made sense, if that answered people's questions, but I'm partly just addressing the fully connectedness and sort of translating what in lay terms or in other books you might see different terms like neuron layer, module, and input, output, and feature. Just trying to make sure that we're sort of all understanding the same, how those terminologies being used.
So this is going to be a little bit, I don't know, maybe I just won't show that. But you can basically just peel off whatever layers you want in a neural network. So what I've done here is I've said I want to grab this first layer. But unfortunately, the one that's run here is the one all the way from my bottom network. So the one that I have actually has 20 neurons. There we go. So it has 20 neurons. So what is actually happening is I have 2 validation samples and it's outputting 20 neurons of output. Just another thing to understand here is you can peel off layers and you can inspect, okay, what's the output from this? But we'll move on from that.
Hey, Ryan, I had a different question. I don't know if this is even worth going into, but you showed that we don't need to define our own loss. There's built-in, mean squared error loss. I noticed that there's this sentence in the book. Let's see here, page 157, where it says loss functions are in the NN module are still subclasses of NN.module. And I was wondering, I understand why activations, of course, would be a subclass of a module, but do you know why losses are a subclass of module?
I'm not sure. I don't fully have my head wrapped around what exactly the intention of a module is. I just know that it can kind of record and capture some information. So I don't know exactly.
Seems like the loss function should be set globally for the whole network, right? It shouldn't be set for an individual layer.
No, you're right. Yes, it is set for the whole thing. It's not set for a layer, but I think maybe this is a programming thing and not a conceptual thing. That like a module is just something that takes tensors and input and spits out tensors and output. And so loss functions do that. They take tensors in and they spit out tensors. And so therefore but I don't know that you would ever think of, again, using other books, other terminology. I don't think you would ever, you can think of an activation as being a layer of some kind, but I don't think you would ever think of loss that way. It's just, but from a programming perspective, it may behave similarly. It has inputs and it spits out an output.
Possibly if
it's in
like maybe if part of your network you want to have something that's more like a regression until you get to a classification layer, then you might want to change to like cross entropy from mean squared error or something. I don't know. That might, I don't know if that makes any sense.
I think I'm with you, Ted, from the standpoint of module is the generic tensor operations. So any operation on tensor is going to be a module because that's the layer that they kind of want people to interface with it at, such that underneath the hood, they can say, okay, this module, when it's run on GPUs, is implemented this way, and when it's run on CPUs, is implemented this way. And so it's really just that bounding box.
So you're just benefiting from whatever under the hood stuff they've abstracted away anytime you subclass from module.
Yeah.
Cool. That was Chris, right? Thank you.
Yeah. I remember seeing it in part of looking at the code, the abstract tree they have.
Mm. So there was a question about should batch size for training match the size for validation. It kind of depends on your network. In this case, it doesn't matter. You could actually have differing batch sizes and it wouldn't make a difference, but it is possibly the case. It just depends how you configure it. If you configure it correctly, batch size shouldn't matter on validation, but you have to do some additional things in order to make that actually happen. So in this case, they don't actually put the model in evaluation mode. And so evaluation mode does a bunch of things, like it freezes batch norm layers, it prevents dropout, it does all of these additional things. So if you put your model in evaluation mode, it shouldn't really matter what your batch size is because it's just capturing what was learned on the previous steps during training. So in theory, it shouldn't matter. There isn't any reason why you couldn't do individual samples rather than batches. So this is just them showing we can print off the sizes of all of the different layers. So we can see the first layer is 1 input, 13 outputs. This is the tan-H activation layer. And then this is taking our 13 inputs and mapping it to one output. And then I think this is our final bias, I would assume. I'm not sure about that one. Yeah. So then looking at the named parameters, we actually get the names that go along with it. And this is more descriptive. So we can see this is the weights and the bias. So this is actually the bias. It's not the activation function. So we can see what the names are that correspond with all of the different layers. And we can see that what was probably number one, the activation function, doesn't have a shape because it's just a function that you're applying to arbitrary numbers, basically. And then they're showing, these are just kind of the predefined names. I believe that the 0, 2, that's all just kind of sequentially numbered. But if you want to give your stuff actual names, you can pass in an ordered dict and then say, okay, I want to name this one hidden layer, this one hidden activation, this one output layer. And you can give those specific names. And so when you print it off, you've got the name associated with the actual layer.
Hey, Ryan, is ordered dict a standard Python
Yeah.
thing?
Yeah. It is.
Sorry, Ted, I don't know if you had some follow-up on that. I had another question. So what is the difference between ordered dictionaries and normal dictionaries? Because I've never used ordered dictionaries before.
Dictionaries, I don't know the fine details of it, but dictionaries have no guarantee in terms of like the order you put things in and stuff like that. And ordered is actually ordered like a list would be, basically.
So the keys
Actually,
stay
they
in the
change
same
it.
order that you inserted them.
They change it in Python 3.7 or even in Python 3.8, I don't remember. But now dictionary is in the order in which you put it at first.
Right, so a regular dictionary now acts like an old ordered dictionary, but PyTorch started before that was available.
Oh, so PyTorch still then requires an ordered dictionary, even though both dictionaries and ordered dictionaries are now the same, if I'm understanding?
Right, exactly. Just because they're a different object type, you import them from from the collections package, and so that's just it's just a different object that it's expecting to see, and it worries if you don't have one.
Gotcha. Thank you.
That way your layers stay in the same order. That's basically why they did it.
Well, the other thing is, I guess that wouldn't be that big of a concern. I was thinking maybe there's some way that they're inspecting the keys and the values separately, and then they might get shuffled or something like that. But I don't think that would actually happen. Yeah, I don't think that's an issue you would run into. So in this one, they're showing we can do the same training loop, but this time we can plug in just a normal nn.mean squared error loss. We don't have to custom define it. And then they can show, here's the process that converges exactly the same thing. Training loss gets this, validation loss gets this. And then they actually plot the predictions of all of the different points. So you can see that when we did our linear model, it was just a straight line that went through the points and it reasonably well approximated things. And with the neural network, we end up with something that's a little bit wavy and actually fits the training points better, but maybe fits the validation points a little bit worse. And so extending beyond that, one of the things they said was try and find something that will just grossly overfit the training data. And so what I did, they gave us a starter thing where they said, okay, here's the number of neurons, here's a couple activations, here's a couple whatever else. They just started with a very basic setup. And what I did is I just copy and pasted a bunch of times and I made it so it's a much deeper neural network. And I was trying to see, can I plug in a different activation function? Can I plug in something else to try and make it overfit a bit more? And so I let it train for a lot more epochs. And so you can see eventually I get a training loss that's really, really low and a validation loss that's significantly higher. And so looking at the training points, which I believe are the X's, it basically perfectly maps to all of the X's. and makes this kind of jaggy line and maps to all of the sensor error that they were talking about, because we're talking about the thermometers still. And so you can see, but it totally misses some of the validation points that I believe are the blue lines. So just a little exercise. If you want to, you can play with this and you can try to find a way that you can get it to fit the training points better and the validation points better. But ultimately, it's not that important of an exercise because this is just a simple linear data.
I had a question. So and I haven't used PyTorch and using Keras in the past. Is that typically how you define things, or are they just doing this, for example, of like the for loop and then going through the step backwards and stuff like that? Or are they just doing this to kind of show you this is how it's done, but this is not actually done in practice?
Are you talking about like defining this training loop thing?
Yeah, that function.
So that's pretty common. Most people, I talked about this a little bit last week, but most people, what they do is you kind of just define one training loop and you just keep that forever. And that's what I've done is I borrowed a training loop from someone else, and then I've just always used it going forward and made slight tweaks on it. But there's also stuff inside of Catalyst and wherever else that kind of more closely mimics what Keras does, where it's like, okay, I just plug in this thing and Keras handles all of it for me. So some people write their own, some people just use Catalyst or Ignite or what's the other one? I mentioned another one last week. I forgot it already. But there's a bunch of them. So you don't actually have to write that code every time, potentially. And it's generally generic enough that you don't have to worry about it too much.
Lightning.
Yeah, Lightning. Yeah, that's one of the major ones too. It's getting a lot of traction. So we covered all of the NN module. I feel like we covered most of the stuff from the notes at least. So this next notebook is looking at the activation functions. We've kind of talked about this in detail a bit already. This is just printing off all of the ones, not all of them, but some of them that it has built in and just visualizing what the graph actually looks like. So TANH, hard TANH, Sigmoid, soft plus, Rayleigh, Leaky Rayleigh. So most people end up using this or this now. And then they're showing, here's all of the different combinations, so you can piece those together across the various different layers and you can get some interesting patterns. That's all you really need to know about it.
Hey, Ryan.
Yeah.
Oh, before you leave that screen.
Yeah.
that figure you were just looking at, yeah, that's set. So the C of, where to go? C of A plus B, and then D of A plus B. So are they, I mean, are they really saying that they're taking, taking that third image on the top, that's a TANH function, applying C, which is yet another TANH function, to get that bottom left diagram? So it's a depth. So I don't know, are they showing that it's the next layer down? I didn't quite get it.
No, so what I would look at it from left to right. So they're showing this is A, this is B. When we add these together, which is literally just adding them across all of the points, this is what we end up with.
Yes.
If that makes sense.
So
yes.
So A plus B would be kind of what you get if you had a layer below A and B and it had weights of 1 and 1. So that is not changing A and B at all.
Okay, so that's, so if you go across the top, that's like figures 1, 2, and 3, 4, 5, and 6. So if you look at figure 7, which says C of A plus B.
Right.
So C is right above it is another TANH function, but then it's A plus B. So I was guessing they were plugging in that number 3 figure.
That's right. Your number 3 figure would be the inputs to C, and then that's the shape that you'll get if you had weights of 1 and 1, just identity weights, and then you put it through the C activation function, so to speak.
Okay, so that then that is right. Okay.
This is conceptual functional. Don't take me overly literally about the weights of 1 and 1, because that's not how exactly the unit works. But in terms of compositing functions, if you literally just add those two and you plug it into that C function, which is not, not technically the definition of the activation, but you get the gist.
Yeah. Just took me a little while poking around the figures to go, what's C? A plus B. What do you mean? A plus B up there? Oh, over there. Okay. And then, yeah.
Yeah.
Okay, thanks.
So this is kind of a bonus notebook, and I think that this one is actually kind of important. So in the previous section, they were showing sequential. And so this is good if all of your layers just go in a perfectly linear stack, and you go, this goes into this, goes into this, goes into this, and then I want an output. But that's not always the case. Sometimes you have different layers that are branching in different paths or being reused in some way. You're saying, okay, I have this CNN layer, I want to apply it to this image and also this other unrelated image, but I want them to share the same weights or something like that. So that's where this subclassing ends up coming in. So this is something that really confused me a lot about PyTorch at the beginning, because I thought you had to do everything like this, and I didn't realize you can kind of stack layers like you do in Keras and TensorFlow. But this is kind of the better way to do it if you're doing something complicated down the line. And so basically what they've done is they've said, we're going to make a new class. It's going to inherit from the model, the module, nn.module. It's going to have an it method.
Hey Ryan, it might just be me, but would you mind making your text a little bigger?
Sure. So we're making the subclass model. And so the important things here that will be common in basically every neural network is you want some sort of initialization step, and then you want some operation of how you're going to use all of those layers that you just initialized. And so this is the way that I at least think of the PyTorch layers is in the init, you're initializing all of your layers. So you're just saying, I want a hidden layer, I want an activation function, I want an output layer. And then when you define the forward, this is actually defining, okay, here's how I'm going to stick all of those together. So I want the hidden layer to take the input, I want that input to go through this activation layer, and then I want my output layer to be applied onto the intermediate activation layer. And so when you do this subclass.model, you're initializing your neural network. You're saying, here's the list of layers that I want to use, and then when you go to actually apply it, you just pass in your input like it's calling a function or something like that. And so that's all they really show. But this becomes useful if you have multiple different branching paths, and it's not as simple as the nn.sequential where you go, okay, these are always going to feed into each other. So they didn't really show anything of too much meat in it on this section, but just something to keep in mind for the future.
Hey, Ryan.
Yeah.
Me again. So you're defining init and you're defining forward there. Mm-hmm. In the book, I'm recalling like section 621 using call rather than forward. So I'm guessing this is a case where you would not be using call, you'd just be using your subclass model.
So you're still going to use call. So it's inheriting from this nn.module, So nn.module is bringing along a whole bunch of stuff, including the call method. And so the call is going to call the forward call. So you still have to define this. But you're going to want to actually call it by just doing that and passing your input. You're not going to want to do that. You still want to use call. It's just invisible because it's being inherited from nn.module.
Okay. All right.
Kind of just a programming detail. I wouldn't worry too much about it.
All right. I won't worry.
I think we'll probably look at it in more detail in a future chapter too, probably.
So is it more complicated than Keras model? And I mean model as functional IP with capital model with capital M?
Yeah, so this is a little bit more complicated in that Keras will automatically figure out the connections for you. In this, you have to just define the layers, and then you also have to define how all the layers are connected. So it's a little bit more complicated than it is in Keras, but it also allows you a little bit more flexibility and customization.
Thank you.
Yeah.
So Ryan, I'm familiar with in Keras, and I apologize to the people here who don't use Keras. You can define a whole new type of unit, and then a layer is just a collection of those units. And so I would subclass off of something else potentially and define a new unit, but then I could still use sequential, or I would still use Keras functional to say, give me 20 of these units in a layer.
Yeah.
But this is very different because this you're actually, you know, you're handling sort of the flow from one to the other. You're not just defining a new kind of unit.
Yeah. Yeah. So it's one of the things that took me a long time to understand about PyTorch after coming from Keras, but it's also one of the things that I think makes it much more powerful, is being able to kind of custom define, okay, I have these layers and I can apply them in any way that I want. So if I really want to, I can just remove a layer, and as long as it actually continues to fit in terms of sizes, there's no problem in that. I can just randomly drop layers. I can randomly pull off the layer and apply something else. I can do all kinds of stuff there.
Yeah, like, so for example, in my bird song thing, I've got, because I started out using canned models, they had 3 channels, red, blue, and green. But since I don't actually have 3 channels, if I were doing my custom thing here, at some point I could just ignore the 2nd and 3rd channels.
Yeah.
Because that's just a waste.
Yeah.
But in Keras, I can't really make it do it because it knows those inputs exist and they don't just disappear.
Yeah. And so I've done a lot of interesting things in the forward call too, where I go, okay, I'm going to do some weird input structure, and then in the forward call, I'm going to kind of unravel it and feed it into different places. And I put that inside of the forward call too, and that's been a big advantage as well over Keras, where it's like, okay, I don't want to organize the data until it's actually in the neural network, and then I'm going to actually place it in all of the correct places. I think that's it in terms of the book. Any more questions, closing comments?
Would you have an example, Ryan, of where you have found it helpful to use like 2 different flows in terms of the networks in parallel? Sounds like you've used this previously, but trying to get a concrete example of how that's, what conditions you might want to consider that.
So one of the important ones is if you have data of mixed types and it doesn't really fit in the shape that you want. So for example, let's say you have text and you've got a sequence of words and you want to tokenize that in some way. And then you also have some numerical data. And so the text data is 50 words by the number of features or something like that. And you have numerical data that's just flat. It's just 10 additional features. It doesn't necessarily line up correctly that you can just stack it and then just pass it to a neural network easily. And so what you can do is you can pass it to the neural network, and then in the neural network you can say, okay, input 0 goes down this lane and input 1 goes down this other lane, and it goes down an entirely different process where one of them is like an LSTM for the text and the other one is just a normal dense layer, and then eventually they meet in the middle and all of that knowledge is combined and utilized. So that's the kind of direction that I've typically gone. And you can go even more complicated than that, where you also have a image branch and they all kind of meet in the middle at some point.
I saw one very concrete example once. It was for house selling. So they had a picture of house, they have a description, and they have some numerical data about it. So it is 3 kinds of data with which they needed to work and to predict what price is supposed to be here, how quickly they can sell it, and such and such.
Interesting. Thank you.
And then there's also the possibility of, sometimes I've done neural networks where you have multiple different things that you're trying to predict. So in one, I'm trying to think of a good example competition. We did one competition where we were trying to do segmentation of, I'm trying to remember what it even was. It was something to do with the lungs. We were looking at the lungs and we were trying to segment some disease. I'm blanking on the name of the disease right now. But we were able to split it up into 2 separate problems. One of them being, does the person have the disease or not? And then the second one being, where in this image is the diseased region of the lung? And so you can actually have your model output 2 separate things. One of them being just a binary, does it have the disease or not? And the second one being the actual mask of where the thing is. And you can just then take those, and it might actually come from a similar region of the network, and it outputs 2 entirely different things, and then multiply them together. And then one of them acts as a gate on the other. But you have this awesome flexibility of having multiple different outputs and multiple different input structures and reusing layers and all kinds of stuff like that. Yeah, I think it was pneumothorax, Tommy.
Neat. Cool. Thank you.
Yeah.
All right, any other questions?
I had a question. So is the flow for TensorFlow much similar to what we're seeing with this PyTorch flow? I'm like trying to wrap my head around it because I'm so used to using Keras, but I'm curious at that level, is it kind of similar?
It's approached a similar solution now, yeah. So in TensorFlow, it's a lot more similar than it used to be, where you're kind of doing the same thing, where you're defining the layers and then you're planning out the path through them. It's pretty similar, actually. I haven't done that much in TensorFlow recently because I've been doing more in PyTorch, and Keras too when I do that. But yeah, I've seen people's work in TensorFlow, and it's approached kind of a similar point now.
Yeah, and I mean, at the end of the day, you're using the autograd functionality for TensorFlow, which is slightly different, but still, it's doing an autograd in order to enable the back propagation.
Mm-hmm.